All right, good morning. So, can you please share the information of tomorrow examination so that everyone will not forget? Di mana pukul berapa? And can you see my screen? Big O notations introduction in 5. So, orang tolong tulis information of examinations for tomorrow. Tempat dan masa. Okay, so we'll see you tomorrow 8:30 malam kan? 8:30 p.m. Come. All right. Okay. So kita akan discuss what will be the important things that you need to focus today. Okay. First, big notations. Kita play video dulu.
Today we're going to learn about Big O notation. So what is it? Big O notation is simplified analysis of an algorithm's efficiency. We cover a lot of algorithms on this channel, and we need a way to compare them and some idea of how long they'll take to run. Big O gives us an algorithm's complexity in terms of the input size, n. It gives us a way to abstract the efficiency of our algorithms, or code, from the machines they run on. We don't care about the stats of the machine. Rather, we examine the basic computer steps of the code. We can use Big O to analyze both time and space. There are a couple ways to look at an algorithm's efficiency. We can examine worst case, best case, and average case. When we're talking Big O notation, we typically look at worst case. This isn't to say the others are unimportant, however. Let's talk about a few rules. First, Big O notation ignores constants. For example, if you have a function that has a running time of 5n, we say that it runs on the order of Big O of n. This is because as n gets large, the 5 no longer matters. In the same way, as n grows, certain terms dominate others. Here's a list, but I'll show you a visual on the next page.
Okay. Dia kata dalam Big O notations, you will ignore the constant. Okay. So kalau 5n's, although you have 5 in front, 5 itu dia akan ignore. So your Big O notations will be Big O notations of n. Okay. Secondly, the same thing for tomorrow, hafal yang ini. Okay, yang mana paling worst? The worst will be n factorial. All right, followed by 2 to the power of n square, n log n log n 1. 1 itu constant lah. So your Big O notations will be the best case. Kalau n Big O notations of 1. Okay, hafal yang ini. It will not given in your exam, okay? So hafal sekarang. So in Big O notations, it will ask you the worst case conditional. That's why you find the highest complexity. Okay, nanti kita ada contoh dalam video ini.
We ignore or drop low order terms when they're dominated by high order ones. Take a minute and
Okay, so ini dia represent in a graph terms. Okay, yang paling senang, the least complexity will be big O notations of 1 or big O notations of log n. Okay, follow like big O notation of n, big O notations of n log n square to the power of n and n factorial. So dia kata yang paling best case adalah yang bawah. Semakin tinggi dia menuju ke atas, semakin kompleks equation itu dan dia mengambil masa yang lagi panjang. Alright. So we are going to look at the example.
Study this chart. It can be found on bigocheatsheet.com along with a handy guide on the Big O of various important algorithms. Let's run a few examples so you can see what I mean by basic computer steps. We'll start with constant time. Imagine we have the following line of code. This basic computer statement computes x, and notice it does not depend on the input size in any way.
Okay, so dalam equation ini, x equals to 5 plus 15 multiplied by 20. Sini dia tak ada apa-apa pun boleh ubah. That is why dia adalah satu constant. So it's going to be big O notations of 1.
We say this is big O of 1, or constant time. What happens when we have a sequence of statements?
Okay, so yang ini, kamu ada beberapa equations. However, although you have a few equations, dia tak jadi masalah sebab dia tak ada pun boleh ubah. Dia semua adalah numbers. Okay? So we see the answer. You can guess, huh?
Notice that all these are constant time. How do we compute big O for this block of code? We simply add each of their times and we get 3 multiplied by big O of 1. But remember, we drop constants, so it's still big O of 1.
Okay. Although you have big O notations of 1, big O notations of 1, big O notations of 1 3 kali, tapi jangan lupa dropkan constant dia. That is why your answer will be equals to big O notations of 1.
Let's look at linear time. Suppose we have the following for loop.
Okay, sekarang kamu ada n, ah? Sekarang kamu ada n. Sekarang kamu start ada pun boleh ubah.
That prints the numbers 0 to n. We know the print statement is big O of 1. This means the block of code is n times big O of 1. In other words, big O of n.
Okay? Bila kamu ada pun boleh ubah n, so dia big O of n. Print x adalah big O of 1. So bila kamu ada big O of 1 dengan big O of n, so your answer will be big O of n. Alright?
Here's another sequence.
Okay, you can guess. Sini semua pun boleh ubah. So it will be big O of 1. When you have n pun boleh ubah. So you have big O of n. Ini adalah big O of 1. That's why big O of n, big O of n, big O of 1, you have your big O notations of n.
First line we know, again, is big O of 1. And the for loop is big O of n. The total time is the summation of these two. But remember, we drop low order terms. When n gets large, the time it takes to compute y is meaningless, as the for loop dominates the runtime. Finally, let's look at quadratic time.
Okay, quadratic. Bila kamu ada nested for loop, okay, you need to run y first, and then you go to x, another x. And then run y, and then go to x. Run y, and then go to x. So, kamu ada n, yang kamu perlu run n times. Okay, kamu ada n di mana you need to run n times, that y is equals to
I think you can see that the print statement will be executed n times n, which gives us big O of n squared. Let's do two more examples covering everything we've talked about. Say we have the following block of code.
Okay. So kamu akan ada programs this way. So di mana boleh ubah itu kamu boleh ignore saja. Alright. Then you have X, sorry. And you have X in order. Tapi kamu kena tahu ini adalah X for yang nested for loop itu ini. Okay, this will show the nested for loop. Atas itu adalah loop satu kali. So yang paling besar you are going into the nested for loop which will equals to n squared.
Code. What is its total runtime? Well, we know the runtime for each of these, so the total runtime is simply the max of the three. The nested for loop dominates here, so we get big O of n squared. How about this if-else statement?
Okay, if-else statement. Alright. So you are going to see dalam ini dia ada X, akhirnya dia ada n squared. Alright. We are going to look into the highest one. Alright.
Pretend the sequence of statements in each clause have already been deduced to the big O's shown. We talked earlier that when we're discussing big O, we usually look at worst case scenario. So for this situation, we choose the largest runtime, which happens to be big O of n squared. I hope this gives you an understanding of big O notation. Let's wrap up by talking about the real world. When you're coding your algorithm, please realize that constants absolutely do matter. A lot of situations have small input sizes, so a constant of 2 or 3 could have a large impact. Lastly, for the same reason, be cognizant of best and average case. Depending on your application, this may be more applicable for your algorithm. As always, thank you for watching. Please subscribe if this helped you. Today we're going to learn about big O notation.
Hello friends and welcome pitch. So it's analyzed. So we have next we drop the const. The first step.
Okay. In your exam is going to give you an equations seperti ini. Okay. Yang rendah itu kamu akan dropkan. Okay. So you are lefting off 2n squared. Bila 2n squared, you are going to drop the constant. So sini answernya untuk your big O notations will be equals to big O notations of n squared.
Is to drop the lower order terms that are 3n plus 1 in this case. Next, we drop the constant that is 2. So we get the time complexity as big O of n square for this particular polynomial. Now, let's look at some rules for finding out the time complexity in algorithms. First, let us look at how do we calculate the time complexity of a single loop, which takes n times time. So,
okay. Untuk ini, okay. Kamu ada satu loop aja. And your loop is you are having n variable. Okay. Constant dalam ini dia tidak mengambil masa yang panjang sebab dia adalah satu constant. Alright. So in this case, when you are having one loop, your big O notations will be equals to big O notations of n.
The time complexity will come out to be C times n. And in big O terms, we can neglect this constant and simply write the time complexity as big O of n. Now, let's look at nested loops. In time to execute.
Okay, the same thing happens bila kamu ada for loop. Okay, you run n times. You run n for n times. You are running n time. You are running n for n times. Sebab itu dia adalah n square.
And for each run of the outer loop, this inner loop will also run n times. So the total running time will be some constant multiplied by n, which is equal to n. So we can say that the time complexity is big O of n square. Then we simply add the time taken.
Okay. Kalau dia constant, you have big O of 1. Kalau dia 1n, you have big O of n. Alright, the same thing over here, big O of n.
Taken for each statement. In big O, how do we find out it?
Alright. Constant, big O of n, kamu jadikan the equations. Okay, the answer will be big O of n. Alright, although you have 2 times of constant n, tapi kalau kamu tambah C2 tambah C3 dia sama satu constant, so you are taking big O of n as the worst case complexity.
When we have conditional statements such as if else, we evaluate the situation when values in if else conditions of n city, and hence the overall time complexity.
Okay, kalau kamu n kat sini, else itu n square, you are taking the higher one, which is big O of n square.
Will come out to be big O of n square. Now, let's look at the comparison of time complexities.
Okay, this one you know,
So,
okay?
we have
Tolong
big
hafal.
O of 1, which is the small. We have big O of n factorial. It is highly recommended to learn them by heart as it comes very handy program. However, space or assuming that an integer total space will come out to be, this comes up between optimal each other and requires a lot of algorithms.
Okay, space complexity, okay? You learn until here, huh? Okay, so hafal
Then
yang ni.
comes big O of n. Then it is big O of n log n. Then we have exponential time complexities. And finally, we have big O of n factorial, which is the worst.
Okay, ada soalan untuk soalan pertama. Tak ada teori untuk soalan ini. Okay, tak ada teori untuk soalan ini. So soalan ini ada akan minta kamu, dia akan bagi equations and then you find the worst complexity. And then ada some questions yang dia akan minta kamu kira masa sikit. Alright, if you can understand well, it shouldn't a problem for you to answer question 1. Boleh?
Here's another example of using Dijkstra.
Alright. So yang tadi big O adalah soalan pertama. Okay, kita skip soalan kedua sebab sorting untuk soalan 2 dengan 4 saya gabungkan sekali. So we go to question 3 dulu, Dijkstra.
This algorithm for finding minimum weight paths between vertices on a weighted graph. For this example, I'm going to start at vertex A and find the minimum weight or short.
Okay. Okay. Ambil perhatian. ambil perhatian. Untuk trajectory, you have some theory questions. Di mana soalan satu itu sebelum dia minta kamu buat trajectory, mungkin dia akan minta kamu list down the steps of trajectory. Atau mungkin dia akan minta kamu draw the flowchart of trajectory. Atau mungkin dia akan panggil kamu write the pseudocode for trajectory. Alright. Saya ulang. Untuk soalan 3, kamu akan ada some theory part di mana firstly dia akan tanya kamu antara satu ini, saya pun tak tahu mana satu. It will ask you to draw the flowchart. It will ask you to draw the pseudocode. Else it will ask you to list down the steps. Which one? Saya pun dah lupa. Alright. That is the part 1. Part 2, let us do together dalam video ini.
Shortest distance paths to every other vertex.
Okay. Untuk trajectory, the aim adalah untuk mencari point daripada A ke semua point dengan distance yang paling dekat. Saya ulang. Untuk trajectory, the aim adalah untuk mencari jarak yang paling pendek daripada A ke semua titik yang ada dalam graf berikut.
Vertex. So starting at A and going to A, of course, doesn't require traveling at all. So I'll get a weight of 0 there. And since I'm finished considering A as a destination now, I've got the shortest distance, I'm going to put a box around it, and I don't have to put anything else in this column underneath it. I can get from A to B with a distance of 8, or a weight of 8, and the subscript means that I just came most recently from vertex A to get here, and these subscripts are going to help us track where the paths go as we move along. I can get from A to C with a weight of 2, and from A to D with a weight of 5. Notice that vertices E, F, G, and H aren't immediately connected to vertex A, so right now they're unreachable, and I'll mark them with the infinity symbol to show that. Now I look back at this row that I've just completed, and I find the shortest distance without a box. So the boxed one we're through considering, but 2 is the next shortest. So I'm going to copy that down to the next row, and I'm going to put a box around it because now I don't have to think about C as a destination anymore. I've got the shortest path from A to C. And I'll mark over here that I'm considering vertex C now. And the next question is, can I get from C to B, D, E, F, G, or H with any shorter path than what I've got so far? Well, I can't go directly from C to B, so that 8 underneath the B column is unchanged. I can get to D, however, from C with an additional weight of 2. Well, 2 is the minimum to get to C, and if I add 2 more, that makes 4. 4 is better than 5, so I'll mark that down here, and I'll put a C as a subscript, indicating that C was the vertex I came most recently from. I can get from vertex C to E with a weight of 5. So 5 added onto the 2 gives me a weight of 7 in total. Again, coming from vertex C. I can't get from C to F or to G or to H, so those are going to remain unreachable. Now the shortest distance or minimum weight that isn't boxed already is this 4, so I'll keep it as my next shortest path here, and it's from vertex C, put a box around it, and so D is the next vertex to consider. Do I have a shorter path to B from there? Well, I can add a weight of 2 to get from D to B. 2 plus 4 is 6, and that is better than 8. So I'll mark the 6, and it came through vertex D. Can I get to vertex E? Yes, with a weight of 1. 4 plus 1 is 5, and that's an improvement over the 7 that we had. Can I get from D to F? Yes, I can, with a weight of 6. 6 plus 4 is 10, so I put the 10 underneath the F column. Can I get to G from D? Yes, with a length of 3. And 4 plus 3 is 7, so I'll put a 7 under here. Can I get to H from D? No, not directly, so I'll still leave the infinity symbol under the H column. Now the minimum weight that isn't boxed already is this 5. So I'll mark that in the next row with a box around it. My shortest path to vertex E comes through D, and it has weight 5. So E is the next one that we're working with. Can I get from E to B? Not directly, so this 6 will not change. Can I get from E to F? No, so that 10 will stay unchanged as well. I can get from E to G, though. So 5 plus 1 is 6. That's an improvement over the 7 that we had. So I mark a 6 here, and we came from vertex E. So that's the subscript. And I still can't get from E to H, so there's still no path yet that brings us to vertex H. So this row is done. Now there's 2 weights in this path that are the same. So 6 and 6. It doesn't matter which one I pick to move forward with. Let's just use the one under B since that's alphabetical order. So I'll put a box around it, and B is the vertex we're working with. Can I get from B to F? Yes, it's a weight of 13. 13 plus 6 is 19. That's not better than 10. So we'll leave the 10 alone. Can I get from B to G? No, so I'll leave the 6 alone. And I cannot get from B to H either, so I'll leave that infinity symbol there. Now the smallest weight that's not used is this 6. So I'll copy it down and box it. And G is our current working place. Can I get from G to F? Yes, with a weight of 2. 6 plus 2 is 8, and that is better than the 10 that we had. So we'll put the 8 down and mark G as a subscript. Can I get to H from G? Yes, with a weight of 6. 6 plus 6 is 12, so I can finally replace the infinity symbol with a 12. Now 8 is the smallest unboxed weight. So I will copy it down to the next row and put a box around it. Vertex F is now where we're working. Can I get from F to H? Yes, with a weight of 3. 3 plus 8 is 11. That's better than the 12 that we had. Now this row is done, and the only thing that's left to do is to mark the 11F here with a box. And now I have all the shortest paths from A to all the other vertices. If I want to know what the path is, which vertices it went through, I just start at the destination. Let's say I wanted to know about this path of 6 to vertex G. It came most recently from E, so it ended with EG. The vertex E had a shortest path to it from D, so it went DEG. And so prior to D, it came from C, and from there, previous, it came from A. So it went A, C, from C to D, from D to E, from E to G. And so that's the path we had to take to get the length of 6, A, C, D, E, G, and I can go back and trace it on the graph. A, C, D, E, G, length of 2, 4, 5, 6. And we could do the same thing for any one of these minimal weight paths that are now in boxes.
Okay. Saya rasa faham. Okay. Part 3 untuk soalan ini. Part 3 untuk soalan ini dia akan tanya the real conditions of Dijktra where you can implement. Okay? Maybe dia akan tanya in real conditions. Maybe dia akan tanya the real conditions is computer. Maybe it will ask you the real conditions in network. Mana-mana. So be prepared of the real conditions of the implementations of the etc. dalam kehidupan harian atau dalam komputer atau dalam programming atau dalam computer network. In network. Alright. So ada soalan untuk soalan 3? Ada soalan, my dear. Tomorrow, complexity esok topologinya lebih kurang macam ini. Alright. It shouldn't be any problem jika kamu menjawab. Okay? Be slow and steady bila buat calculation. Alright. So the third one, the second question and the fourth question will be based on sorting. Okay? Untuk soalan 2, sortingnya dia akan minta kamu buatkan algorithm dia. Okay. Soalan 4 dia akan bagi numbers and then you do the sorting dengan cara yang kita tunjuk. Okay? Dalam video. Okay? I think you have looked at the video already. Okay. We revise through the video. Okay?
Today we're going to learn bubble sort. Here's what we'll do. We're going to compare consecutive items. If they're out of place, we'll swap them. The highest number will bubble its way to the right with each iteration. A sorted partition will form at the end of the array. It's pretty simple, so I'll be quiet and let you watch. Done with the first iteration. 9 is now in the correct spot. Let's continue. You get the picture. I'll see you at the end of the algorithm.
Okay, untuk bubble sort, dia akan bandingkan dengan yang sebelah. Okay, jika yang sebelah itu adalah lebih besar, dia tidak akan sort. Okay. Jika sebelah itu dia adalah lebih kecil, dia akan sort. Okay. So then it will exchange and then it will sort until the end.
We're done. Our array is sorted. Here's the pseudocode for bubble sort.
Okay, pseudocode untuk bubble sort. All right. I would like to see the for loop and then the exchange jika dia lebih besar. Okay, I would like to see the for loop and then it will exchange jika dia lebih besar. All right. Okay, we go to the second one, insertion.
Today we're going to learn insertion sort. Let's dive right in. We're given this array and we want it sorted in increasing order. Here's what we're going to do. We'll start at the left and work our way to the right, examining each item and comparing it to the items on its left. We'll then insert it in the correct position.
Okay, the same thing. Untuk soalan 4, jika satu algorithm itu dia keluar, it will ask you to list out the steps. All right. So make sure there is some theory part on the sorting part. Okay.
In the array. You'll notice that part of our array will be sorted as we progress. We'll mark those items with the green background. Let's begin and you'll see what I mean. We start at 2. Of course, there are no items to the left of 2, so we mark it as sorted. Moving on to 8, we compare it to 2 and leave it where it is. Our first 2 items are now sorted. Next, we have 5, which we can see is out of place. We know it needs to be after 2, so we swap it with 8. Our first 3 items are now sorted. On to 3. Again, it's out of place. We swap it with 8 and 5 until it's in the correct position.
Okay. Untuk insertion, selepas dia sort, dia akan sortkan number itu ke tempat yang betul. Alright.
We're at our 5th item, 9, and I'm sure you can see that it's in the correct spot. Let's move to 4 and insert it in the correct place in the array.
That is why kalau untuk insertion dia satu sorting, satu iteration dia habiskan sorting itu.
And that's it. We're done. Insertion sort is one of the most straightforward sorting algorithms. For your reference, here's the pseudocode.
Okay, that is why untuk insertion you have satu for loop. Okay, satu for loop. And then you are going to say that is it greater than, it is swap, then yang number itu akan ke 4 yang sepatutnya. Alright. So you have one loop for insertion. Okay, merge.
Today we're going to learn merge sort. A few quick points, then we'll get to the example. Merge sort is usually done recursively. When you think of merge sort, as with other recursive algorithms, I want you to think of divide and conquer. We're going to break our problem into smaller problems in order to solve it. Let's get started. We have the following array and we want it sorted. We're going to continuously split the array in half, our divide step, till we are left with the individual items. Watch and see. Our array is now broken down into individual items. One note before we start sorting. When you implement this in code, these steps will be done in a different order because of recursion. But I think this human-friendly order provides more clarity in learning. Let's continue. We're ready to sort. We'll examine the individual items, compare their values, and merge them into temporary arrays.
Okay, bandingkan dua-dua. Okay. Groupkan into two and then you do the sorting. Okay,
The
then merge.
temporary arrays are sorted, but
Then-
there's work left to do.
Then
Let's
merge.
jump up the recursion stack and continue.
Okay, then merge
Convert our
it.
smaller arrays into a larger one, inserting items in the correct order.
Okay, merge it kepada 4. Arrange while you are merging. Merge it
One
all
more merge,
together.
and we'll have our sorted array. And that's it. Our array is now sorted. Here's the pseudocode for merge sort.
Okay, merge sort
On the
untuk
left, you have
pseudocode. Merge sort untuk pseudocode dia akan bahagi kepada 2. Satu adalah untuk memecahkan sorting dia itu. Alright. And then you are going to merge one by one and do comparison. Alright. Dia panjang sikit. Okay. Dia pun habis dalam satu, it will have only one iteration. Dia tak ada iteration yang banyak. Alright. So it will finish. Okay.
Recursive part, which halves the arrays. On the right is the merge function, which combines the arrays. Merge sort has a worst case time complexity of big O of n times log n.
Okay, quick sort.
The easiest. Today, we're going to learn quicksort. Like merge sort, quicksort is a recursive algorithm. However, when you think of quicksort, I want you to think of the word pivot. Pivot is simply one of the items in the array that meets.
Okay, jika soalan ni keluar dalam exam, pivot akan diberi ya. Or else bila saya makin itu menangis saya. Alright. Pivot akan diberi jika soalan ni keluar dalam exam.
The following 3 conditions after we sorted it. First, the pivot is in its correct position in the final sorted array. This means that all items to the left are smaller and all items to the right are larger. Let's look at an example. We're asked to sort the following array. Let's choose a pivot. I'll explain the best way to do this later, but for now, let's just choose 3. First, we move the pivot to the end of the array to get it out of our way. Next, we're going to look for 2 items. Item from left, which is the first item starting from the left that is larger than our pivot. Second, item from right, which is the first item starting from the right that is smaller than our pivot. Starting at 2, we can see that 6 is item from left. Now starting at the right, we see that 1 is item from right. Let's swap item from left with item from right. We repeat the process. This time, 5 is item from left and 0 is item from right.
Okay, you stop.
Again, we swap the 2. One more time. This time we see that item from left has a greater index than item from right. So we know we're done.
Okay, bubur 3 dalam tengah-tengah.
We swap item from left with our pivot. Three, our pivot is now in its correct spot. To prove it, let's review our 3 conditions. As you can see, all items to the left are smaller and all items to the right are larger. We said quicksort is recursive. Let's go through the process one more time with the larger partition we just made. We'll choose 7 as our pivot and move it to the end. I'll let you watch without voiceover. Now we have 3 and 7 in their correct positions. I think you understand the concept, so we'll let recursion handle the rest. One important question is, how do we choose the pivot? This makes a large difference in the performance of the algorithm, as we want to choose a pivot that divides the array in half, or as close as possible, to even out the work. One popular method is called median of 3. In this method, we look at the first, middle, and last elements of the array. We sort them properly and choose the middle item as our pivot. We're making the guess that the middle of these 3 items could be close to the median of the entire array. And as you can see, it's not too far off. Here's the pseudocode for quicksort.
Okay, untuk quicksort, okay, you have only one for loop. All right. And then you are going to show how it sort. All right. So the same, just to inform, jika soalan diberi, PV akan diberi.
Quicksort has the worst case time complexity.
Okay, radix. The same thing jika soalan ini diberi, make sure that all the numbers you have three digit lah. Contohnya kalau 45, jadikan dia 045. Okay? Kalau 75, jadikan dia 075 supaya kamu tak buat silap dalam examinations nanti. Alright? Make sure if it has 3 digit, make sure that all the numbers you have, you make it 3 digit. Contohnya 2 ni, jadikan dia 002 supaya kamu tak confused. Alright? Okay, the same thing radix sort, satu sorting saja. So you have only one for loop, alright? Okay, selection.
Today we're going to learn selection sort. Let's say we're given the following array and we want it sorted in increasing order. How will we do this? During each iteration, we'll select the smallest item from the unsorted partition of our array and move it to the sorted partition. We'll keep track of the current minimum and current item with red and blue arrows. Let's get started. We always set the current minimum to the first number in the unsorted partition, in this case 2. We progress the length of the array looking for a smaller number.
Mencari number yang lebih kecil daripada 2.
We find 1 at the end of the array and set it as our current minimum. We swap 1 and 2. We now have 1 item in our sorted partition. Moving on, we set 8 as our current minimum and scan the remainder of the array for a smaller number, updating the current minimum as we progress. At the end, we find 2 and swap it with 8. We're ready for the next iteration.
Okay, selalu mencari yang
3
paling
moves
kecil.
into our sorted partition.
So you only have one sorting saja, huh? One iteration.
Let's watch the rest of the algorithm play out.
Alright, jika soalan ni keluar esok, saya nak tengok step by step sah. You don't jump, okay? Step by step, you sort it for me. Alright?
Pretty simple. With each iteration, you select the smallest item that hasn't yet been sorted.
Okay. So dia akan mencari, okay, the minimum and then it sort, okay? And then dia ulang dia punya proses sampailah satu array itu disortkan. Alright? So this will be the code. Okay, lastly, we go to shell. Okay. So for shell loop as well, you need to have the for loop. Alright. Where you divide it into 2. Okay. Find the temporary, do the sorting, and then arrange it. Alright. So, ada soalan lain untuk esok? Any question you want to ask me sekarang?
Madam,
Ya, saya.
kiranya untuk bahagian sorting ni salah satu ke keseluruhan tu akan masuk?
Okay. Untuk soalan 2, kamu akan ada 2 sorting algorithm. So you need to do 2. Okay, daripada 7 tadi saya tunjuk, dia akan ada 2 keluar untuk algorithm which you need to write the program. Okay. Untuk soalan 4, kita ada 1 sorting saja. Okay, heap tak ada. Shopify. Ada soalan lain?
Madam, satu lagi nak tanya. Untuk soalan sorting ni, kami nak kena ingat juga ke dia punya kod tu?
Kod itu akan keluar untuk soalan 2. Daripada 7 yang saya tunjuk tadi, 2 akan keluar.
Oh, 2 akan keluar. Oh, so tak perlu ingat kod lah maksudnya.
Perlulah, kamu perlulah tulis kod dia nanti.
Oh, kena tulis juga. Okay.
Ha. From 7 to yang mana 1 tu Mak Sarah? Apa maksudnya from 7 to 7 kamu study. Okay? Sebab dari 7 itu dia akan keluar 3. I believe some of you have pasir in your hand. You have pasir in your hand. Soalannya lebih kurang sama, tapi dia akan jadi sorting yang berlainan. Contohnya dalam tangan, I'm not sure, maybe you have radix sort in your hand, but in your exam, maybe it will going to be the other sorting. Alright? You can do pasir as your exercise, tapi sortingnya akan berlainan. Kalau untuk Dajjatra, dia punya topologi akan berlainan, okay? Untuk Big O, dia punya equations akan berlainan. So study 4 yang saya kata, yang lain tu jangan study. Jangan pula saya kata nanti. Okay, you don't tell others we are having the class today because saya pun tak record. Alright.